All right, this is Fluid Dynamics and Acid Base Holes textbook chapter 2. It's late, but a teacher's job never ends, so I'm recording a lecture here for y'all. Let's go through this quickly and efficiently. So you'll hear us talk throughout the class about concentration of solutions. There's all different kinds of units. That's not the important part. But concentration, we're talking about an amount of something over a volume. So per liter is fairly typical. And you may often see it represented as a percent, possibly, or as just milliosmoles, for example, 300 there. That's concentration. So some brief background stuff. This is just review from regular bio. Osmosis is the movement of water from a high amount of water to a low amount of water. In this case, you see the green particles, or water is going to move into the interior where there's lots of green particles dissolved, whatever those things may be. Here you see another case where what is going to happen? Well, all the green particles are on the outside now, so water is going to move from where there's a lot to where there's a little. In this case, water is going to move out. Another way to say this, to give you an idea, and we'll talk about this here in a second, going back, is there's a higher concentration of green particles in here, meaning there's less water per unit area. So water is going to move inward, or water moves towards where there's more stuff dissolved. Easy way to think of it. So here again, water is going to move towards where there's more stuff dissolved, which is outside the cell. Another way to say more stuff dissolved is hypertonic. So here we have a hypertonic solution on the outside of the cell. The concentration inside the cell is 0.9%. Outside is 3%. That means the outside solution is hypertonic. And so water is going to flow out towards where there's more stuff dissolved. In this case, if you put cells actually in a hypertonic environment, the cell's plasmolyse, which is a strange way of saying that the plasma membrane shrinks in as water exits. So the cell gets smaller and shriveled, essentially. Here we have the opposite case where the interior of the cell is hypertonic and the solution is hypotonic on the outside, and water goes towards the hypertonic, or where there's more stuff dissolved once again. The solution is hypotonic. Hypo means below. What happens when you put a cell in a hypotonic solution? It swells and gets bigger. If it's an animal cell, it very well could pop, could lyse. Lyse means to pop and die. If it's a plant cell, for example, there's a cell wall that it doesn't have any effect because the cell wall holds it in. Now in isotonic solution, you can see these arrows. It's equal both directions, in and out, and I want to make sure that you understand that in an isotonic solution where the concentration inside and outside is the same, the flow of water is constant, back and forth, and we call this a dynamic equilibrium. The system doesn't stop. There is no flow of water whatsoever. There is flow. All the time. It's a dynamic equilibrium, back and forth, but it's about equal. So here's a few sample questions. From this point on, you're going to see some different types of sample questions, and I'll encourage you to pause and answer before you go on, before I give you the answer here. So be near the pause button, so to speak, or be ready to pause this video as you go through. So here's a sample question. Which way will fluid move? You would have just paused the question here, the video, and you'll see that water is going to flow towards the higher concentration, 310 milliosmoles. Next question. Here's an application problem, applying what you just learned. After reading this question, you're going to want to pause before I give you the answer so you can answer it yourself. Michael has recently started working outdoors in the hot weather to earn money for his tuition. After a few days, he experienced headaches, low blood pressure, and a rapid heart rate. His blood sodium was down to 125 milliequivalents per liter, which is, again, a concentration. The normal is 144. How do you explain this? You would have just paused, and the answer is essentially, Michael lost sodium by perspiration. Just so you understand, water likes to follow salt. So if he loses sodium by perspiration, water is going to follow as well, and it's going to dehydrate him. The low sodium in his blood allowed fluid to move into cells by osmosis, because now his cells are going to be more concentrated or hypertonic compared to his blood. Lack of fluid lowered his blood pressure and gave him a headache. The increased heart rate was his body's way of trying to increase blood pressure. Sounds very familiar, just like the Underhill problem we set up. Next question. Be ready to pause once again. Frank has hypertension. His doctor advised him to eat a low-salt diet. That's fairly common. Frank consumed a lot of salt the day before his last checkup. His blood pressure was up. Why? Go ahead and pause. Answer yourself. Correct answer, extra salt that he ate made his blood hypertonic. The hypertonic blood attracts fluids from body cells by osmosis. This is essentially like eating a meal full of soy sauce. The soy sauce makes you bloated. You hold on to a lot of water instead of peeing it out, so you carry extra water weight, so to speak. All right, electrolytes versus non-electrolytes. This top one here is an electrolyte because this breaks down into solution into multiple parts where these are going to serve various functions. Glucose is not an electrolyte because it doesn't break apart in solution. Simple as that. Carbon dioxide and acid, so acid bases. This is important. We'll see this again when we talk cardiovascular and respiratory systems. When you take CO2, carbon dioxide, and it mixes with water in solution, they dissolve together, it forms carbonic acid. And carbonic acid gives off one of these hydrogen ions. Here is an H+. Anything that gives a hydrogen ion off to a solution is an acid. And the more hydrogen ions it gives off, the more acidic it's going to be. So carbonic acid is a weak acid, but it's an acid. So as it builds up, it lowers the pH or makes your bloodstream more and more acidic. Okay, so more carbon dioxide equals more acid and thus a lower pH. What do? If you breathe slower, you're going to retain more CO2 and your pH will decrease, or more acid. Okay, and the contrast, if you breathe faster, you will eliminate more CO2 and your pH will increase, or if you like, less acid. Okay, so here's a scenario. Be ready to pause. Blood pH drops to 7.3. How does the body compensate? Now keep in mind that typical blood pH is about 7.4, and those little minor changes are very important or a big deal. So it drops to 7.3. How does the body compensate? Well, your correct answer, you're going to breathe faster to get rid of the carbon dioxide, and thus you're going to eliminate the acid to bring the pH back up to 7.4. The opposite scenario, blood pH increases to 7.45. How does the body compensate? Well, of course, you got the right answer. You breathe slower so that you retain more carbon dioxide. You retain more acid. Okay? All right. John is taking narcotics for pain. The narcotics have depressed his breathing rate. What will happen to his blood pH? pH will decrease because he'll retain excess carbon dioxide, and this will increase the amount of acid in the blood. So once again, pH is manipulated by the hydrogen ion concentration that's given off. When it gives hydrogen ions off in solution, it makes something more acidic, or it lowers the pH. There are, however, in your system buffers, and buffers help to regulate pH. They resist changes, and they do so by binding those hydrogen ions. So if an acid gives off a hydrogen ion, a buffer will absorb them to prevent them from floating around in solution and making the solution more acidic. So buffers prevent large pH changes when an acid or base is added. So strong acid releases lots of hydrogen ions, like hydrochloric acid is readily broken down in water and releases lots of hydrogen ions. A weak acid only releases a few hydrogen ions. Carbonic acid is a weak acid, so you know. So buffers can actually change strong acids to weak acids, again, because they'll absorb some of the excess hydrogen ions. For example, here we have HCl, a strong acid, and NaOH, this is sodium hydroxide or bleach. And you combine them together, and HCl becomes a weak acid and a salt. So you neutralize the acid a little bit by minimizing how many hydrogen ions will come off in solution. Now, medically, if you have acidosis, you have a pH below 7.35. And one of the negative effects of this is that it's going to depress the nervous system, and under extreme conditions or long-term can cause a coma. Acidosis is bad. Alkalosis, the opposite case, above 7.45. This is going to overexcite the nervous system, and you're going to spasm and have convulsions long-term. Also, alkalosis, or too basic, is bad. And we are done.